Here in this question, 4 graphs are given and we have to identify the graph which contains Hamiltonian path. In order to solve this problem, we have to know what is a Hamiltonian path. Hamiltonian path is a path in an undirected graph which visits each and every vertex exactly once. So it is a path in an undirected graph which visits each vertex exactly once. Exactly once. So if we see the first graph 1, let us write vertices first. It contains 6 vertices named A, B, C, D, E, F. So here we can draw a path which exactly visits each vertex exactly once. Let us start from A. So here there is a path from A to B, then C, then F, then E, and then D, and then so we can stop here. Why? Because here all the vertices are visited exactly once. So we can say graph 1 contains Hamiltonian path. So let us try for second. If we try for second, let us see for the second graph. If we try for second graph, we cannot draw a path which visits all the vertices exactly once. Let us start from A. So if we go like this from A to B and B to C and C to G, here we cannot come back. Why? Because if we come back, C will be visited twice. So this is not a Hamiltonian path. Let us start from B. So if we go like this towards A, then we cannot return back. Why? Because here then B will be visited twice. So if we try all the cases, we will not be getting Hamiltonian path in graph 2. So this is not a Hamiltonian. This graph doesn't contain any Hamiltonian path. So let us try for third graph. If we start at vertex D in this graph, we can visit D, E, and then B. Let us say B. After B, C and G, and we have to come back in order to visit either vertex A or F. So then C will be visited twice, C and B. So here graph 3 is also not a Hamiltonian graph. Graph 3 will also do not contain Hamiltonian path. Let us try for graph 4. Let us draw the vertices first of graph 4. Here it contains 5 vertices named with A, B, C, D and E. So let us check if it contains Hamiltonian path or not. So let us start from vertex C. So from C to D there is a path, and uh, from D to B there is a path, and from D to E there is a path, and from D to A there is a path. So here we can find the path which visits each and every vertex exactly once. So we can say graph 4 is also Hamiltonian. We can say graph 4 also contains Hamiltonian path. So here among 4 graphs, only 1 and 4 contains Hamiltonian path. So here correct option is option D. Question: a partial order relationship is represented by a Hayes diagram, and we have to check if it is a lattice or not. For a partial order set to be a lattice, each and every pair of elements should have unique least upper bound, unique LUB and unique greatest lower bound, unique GLB. So if you see the elements B and C, for B and C, D and E are upper bounds and they are not unique. That means for B and C there is no LUB. LUB should be unique and GLB also should be unique. Both LUB and GLB, least upper bound and greatest lower bound, if exists, they should be unique. So here for B and C there is no least upper bound, hence it is not a lattice. So here correct option is option C. It is not a lattice as B and C does not have least upper bound. This is the correct option. In this question, system of equations is given and we have to find the nature of the solution for that system. So if we observe the second equation, if we simplify this one, we will be getting 2x plus 3y plus 5z is equal to 20. And first equation is 2x plus 3y plus 5z is equal to 30. That means here same equation derives two different values. So this is not possible. So here we can say that there won't be any solution for this system. So here the correct option is option A.
Consider the following push-down automata, that is PDA. It is given in the diagrammatical state diagram representation. So initially you take a Q0 as the starting state. Q0 on input A, when the stack symbol is Z, it is pushing 2A's onto the stack. That is the representation. When input A, when A is encountered, when small input A is encountered and top of the stack is A, then it is pushing 2 more A's. When epsilon encounters, it is keeping Z as it is. And again, when epsilon encounters, it is going to the final state by keeping Z as it is. And in response to B, when top of the stack is A, it is making the stack empty. That is epsilon. Lambda here it indicates the null string. That means that particular top of the stack will be popping. Again, there are two paths. This is one path and this is another path. In this path, when small a is encountered, it is keeping Z as it is for 3A's. So it will accept 3A's. So A. For 3A's, it is going to final state in one path. In another path, it is pushing 2A's for each A and popping A's in response to B's. For each A, if two capital A's are pushed, then number of B's that should be recognized by the time when you get the final state or empty stack will be each one A should be popped. So that A cube is one path, that is a string of 3A's. The another path is some number of A's followed by some number of B's, where number of B's is a multiple of 2 into multiple of number of A's, that is m is equal to 2n. Option C is the correct option here.